Welcome to the wrap-up video for Chapter 16. We are going to start with the rest of the PowerPoint, that we did not finish in class. We got about 5 more slides, maybe 6. Finish that off, and then we're going to do some problems in Chapter 16, some additional problems that we did not do in class. We've done quite a few, but I did select an additional 6 problems that represent the topics that we covered. So to give you a little bit more practice. All right, so we left off with, we did not cover this material on, and it is factors affecting acid strength, and we have touched on this in the lecture already. What makes an acid is the pulling of electron density away from hydrogen by something with a high electronegativity. So what we have pictured here on this slide is a representative of the periodic table and in the nonmetal region, because it's metals that produce essentially with water or oxygen produce bases, and nonmetals with oxygen and nonmetals with oxygen and water produce acids. Now, so as we go across the table with hydrogen attached to a nonmetal, we see that the acid strength is increasing, and the reason why is because the electronegativity of those atoms is increasing. And that is the first bullet. The more polar the HX bond is, so X being some other element other than hydrogen, or weaker the bond, the more acidic the compound. So as you're going across the table, it's higher electronegativity that contributes to increasing acid strength. As you go down the columns, the atoms are getting larger, so the effectiveness of orbital overlap, atoms are getting bigger, so the orbitals cannot overlap as well, so the bonds in general get weaker between hydrogen and the other element. So that is those 2 reasons why HF. You may have wondered, why isn't hydrogen fluoride a strong acid like the rest of the halogens in group 7? Hydrochloric acid is strong, hydrobromic acid is strong, and most books label hydroiodic, HI, as a strong acid as well. 2 reasons why with HF. 1, you would think that it being the most, fluorine being the most electronegative atom on the table, that it would have the most polar bond and would be a strong acid. But it's the strength of the bond between those 2, they're very small atoms, that keeps the hydrogen from being lost or given up by HF. And so therefore HF is a weak acid, and as you can see there, it has a Ka of 6.8 times 10 to the minus 4. Whereas HCl right underneath it is a strong acid, and we don't even have a measurable K for HCl. Okay, other things affecting, so the same ideas, applying them to oxyacids. So what we talked about in the previous slide were binary acids. And those are named by saying hydro, and then if it's Cl, chloric, bromic, hydrosulfuric for H2S. These are named from the polyatomic ion that they come from. So what it's saying here is that the more electronegative the atom is that is bonded to the OH in these oxyacids. So down here at the bottom, they're comparing chlorine to bromine to iodine in the oxyacid series where you only have 1 oxygen. And you see that acid strength is decreasing, looking at the Ka, and I have a feeling that y'all are just still not getting this relationship between the magnitude of K and when we talk about strong acids and so on and so forth. The bigger the K, the more products you have, and if you're talking about an acid, the more products you have, the stronger the acid. Because the thing that makes it an acid is the losing of the H+. In our most, common way of looking at acids. If you don't lose the H+ because you've got mostly reactants, as in the case of every one of these acids on this slide, then you don't have a whole lot of H+ around. But comparing them, you do see a huge decrease in acid strength, judging from the Ka, due to the decreasing electronegativity as you go from chlorine to bromine to iodine. So the element that is bonded to the oxygen and hydrogen in the oxyacids, as that element is more electronegative, the acid is going to be stronger, pulling electron density away, which is showing in the diagram here, so that the hydrogen is easier to lose, by water coming along and snatching it away. And then, of course, the more, if you're comparing just chlorine oxyacid series, and for many of these oxyacids, you have at least 2, if not 4 different ones. And again, it comes from the polyatomic ions. So we are representing here a hypochlorite, chlorite, chlorate, and perchlorate. Put a hydrogen on those and you have the acids. And then those are named by changing 8 endings to ic and 8 endings to us. All right? So as you have more and more oxygens, which are highly electronegative, of course you're going to increase in acid strength. Look at the difference between hypochlorous with a 3 times 10 to the minus 8 K, and then you go to chlorous acid, which only has 1 more hydrogen, and you get a huge 1 million increase in acid strength. And then you go to chloric and perchloric, and those are 2 of our strong acids with Ks that we really cannot measure because you have almost all products. Essentially, you do have all products. That's what the definition of strong is. All right, so more oxygen you have, the stronger the acid. And then one other thing that is going to affect acid strength, and that is whether or not you have when you have a carboxylic acid, and I'm going to talk more about this when we get to the examples. Resonance in the conjugate base left behind after you lose the hydrogen makes that molecule, that conjugate base, even stronger. Okay, makes it more stable. So if you are making a product, so if we take a carboxylic acid, we lose the hydrogen, you're left with this conjugate base that you're looking at here. The more stable that product is, the more likely you are to make that product. More stable means you're lowering in energy, and we always push towards that in the real world. And then there's 2 slides here on Lewis, acids and bases. We have touched on those, and in this course, that's really all we do with Lewis acids and bases. If you go on to organic chemistry, you will be sick of them. But Lewis acids are defined as electron pair acceptors. So here you see boron with an empty orbital, because it's only using 3 out of the 4 available orbitals it has in its valence shell. Boron is one of the exceptions to the octet rule. It will be okay with 6. So it's got an empty orbital. And here comes the base, nitrogen. Remember, we've talked about nitrogen being common in bases. Nitrogen has a lone pair. The bond that's formed between the base and the acid actually has a couple of different names. It is called a coordinate covalent bond. And when we talked about those metal ions being surrounded by the water molecules, making a complex, in class, that's exactly what we were referring to as well. The metal ions have many, iron was the example, have many empty orbitals generally, or a few anyway. And so they are able to take electron pairs, definition of an acid, Lewis acid, from an electron pair donor, which is the definition of a Lewis base. So when you are trying to identify Lewis acids, look for metal ions, look for boron, look for H+. Those are all species that have empty orbitals. For Lewis bases, you're going to look for things with lone pairs, negative charges, nitrogen, oxygen especially. Now, it says here, and I'm going to go back to the previous slide because this is, here. Anything that could be a Bronsted-Lowry base is a Lewis base. I've told you that before, but the opposite is not true. And that last bullet here says Lewis bases can interact with things other than protons. So you can't go from Lewis base and say that if it's a Lewis base, it's a Bronsted-Lowry base. Because if you're Bronsted-Lowry, you must have a proton. And that's what that last bullet is essentially referring to. So you can have the vice versa. All right, and here's our practice to finish off the PowerPoint, and then we'll do those extra problems. All right, so which of the following is a stronger, I'm going to bring this into where I can write. I've already done that, so let me quit the PowerPoint. All right, here we go. Almost. There we go. Which of the following is a stronger Bronsted-Lowry base, HClO or HClO3, or HClO2? Well, we just talked about factors affecting acid strength, and I've got three oxygens here versus 2 oxygens here bonded to the same central atom. So the stronger acid is going to be the one with the larger number of oxygens. Now, which is the stronger Bronsted-Lowry base? Here we have to, now these are conjugate bases that come from acids. So in order to think, if we don't think about HS minus or HSO4 minus as bases, I know I've listed them as amphoteric substances and so on, but when you're asked about a conjugate that comes from an acid, you really need to think about the acid it came from, because it's going to be the opposite. So HS minus came from H2S, and HSO4 minus came from H2SO4, from sulfuric acid. Well, sulfuric acid is a really strong acid, so HSO4 minus is going to be a very weak, in fact, it has almost no chemistry. Well, it does have chemistry, but it's very weak. H2S is a weak acid, therefore its conjugate is going to be stronger. So sulfuric acid, strong acid, weaker conjugate base. Hydrosulfuric acid, H2S, weak acid, stronger conjugate base. So the stronger base here is the HS minus, and you really have to think about it in terms of the acid it came from. Explain the following observations. HCl is a stronger acid than H2S. Well, two things going on here. One, chlorine, hydrochloric acid, is one of our 7 strong acids, and I know mine, and you should know yours. So of course it's a stronger acid, but can we explain that in terms of electronegativity? Chlorine has higher electronegativity than sulfur, and that very first slide we talked about in the this last little bit is exactly what's going on here. It's because of the higher electronegativity of chlorine than sulfur. Okay, same thing is happening in B. You've got an oxyacid, you've got 4 oxygens on this one and 4 on this one, so it's not the oxygens, it's not the number of oxygens, it's the electronegativity of the central atom. And phosphorus is higher up in its column than arsenic is, so it has a higher electronegativity. Now, that table that we looked at on that first slide were for binary acids. These are not binary acids. Okay, these are oxyacids. All right. C, that is bromate ion, so this is bromic acid. That's 3 oxygens there versus bromous acid, because that's the bromite ion. So 2 oxygens versus 3. Of course, the one with 3 is going to be the stronger acid. H2C2O4 is stronger than acid than HC2O4 minus. This is, you are looking at an acid and its conjugate after it's lost 1. So you're looking at a Ka1 essentially versus, and here's the same acid after it's lost 1 proton, and essentially it could be a base as well, but you're looking at the second hydrogen. Okay, we talked about this and looked at this on the slide in the PowerPoint where we looked at polyprotic acids, this being one of them, meaning that you have more than 1 hydrogen to lose. The first one is always going to be stronger. This K is going to be larger than that K every time. All right, E, benzoic acid, is a stronger acid than phenol. Okay, this is a carboxylic acid. This is not. So how do you recognize carboxylic acids? This little ending right here, this COOH at the end, means carboxylic acid. It can also be written as CO2H. And this acid has that stabilization of the conjugate, the resonance, in the C. So you got C6. So essentially, I'm going to draw these down here. You've got, this is what they look like. Benzene, don't worry about that. That's the C6H5. And then you've got C double bond O. This is the carboxylic acid group. Okay, so here's the benzoate. ion after it has lost its hydrogen. Let's draw it before the hydrogen, okay? This is benzoic acid. This species has no resonance, so no resonance because of this bond right here. That keeps resonance from happening, all right? That double bond cannot move here. But once I've lost the hydrogen to produce the conjugate, then I can get resonance. So that's what that's all about. That means that the oxygen can be here or here. That double bond can be here or here. That gives you this stabilization. We'll show it as a delocalization, sounding like an organic chemist, of this species, the negative charge. This is very stable. This makes it stable, so you're pushing it towards products because of that stabilization. Phenol, this other species, looks very similar, but it is not a carboxylic acid. In fact, it's an alcohol. Alcohols are weakly acidic. You do have, so it's the same ring as this one. I didn't draw it very well. So you do have a hydrogen that can be lost. It's attached to an oxygen, but you don't have the stabilization in the conjugate in phenol that you do in the carboxylic acid. So that is why benzoic acid is stronger. All right, based on their compositions and structures, so looking at the same kind of thing here in 18, and I'm going to do some erasing because we've got way too much going on here. Just a little cleaning up. So we're going to be looking at how things are put together, and we're going to be looking at acids and conjugates, or bases and conjugates to select. We're looking at bases, so we're going to be looking at acids. Select the stronger base. So what you want to think of, again, you're looking at conjugates here, so you want to think about the acid they came from. In A, nitrate comes from nitric acid, nitrite comes from nitrous acid. This is a strong acid, so its conjugate, nitrate, is weak, often a spectator. So that makes nitrite, which comes from nitrous acid, the stronger acid. All right? Base. PO4 versus ASO4. So again, you want to think about the acids they came from. So this is the way we need to think. The acid that PO4 comes from is HPO4 with a -2 charge versus HASO4 with a -2 charge. If you look up the K, and it would be Ka3s, because these are both triprotic acids. If you look up the Ka3s for each of these, the Ka3 for this species is larger, so that makes this weaker. This is the stronger base. Now you would think phosphorus having the higher electronegativity would make it the stronger acid. It's when you start losing multiple protons, things are not as simple any longer. So you really have to look, again, you have to look at the acids they came from. You would be comparing Ka3 of this acid to this one. This one has a higher Ka3, which makes its base weaker than this one. Okay? And then last, we have HCO3 minus versus CO3 -2. So what we're dealing with in C is in HCO3, that comes from H2CO3. So that's Ka1 for carbonic acid. This comes from HCO3, and that's Ka2. The first proton is always stronger than the second, so this K is always larger than that. That makes HCO3 minus a weaker base, so carbonate is the stronger base. All right, next, identify the Lewis acids and bases. So looking for empty orbitals, looking for species with negative charges. Here's one here, negative. These negatives are hard to see on both the hydroxide and the bromide. So in A, what is acting as a Lewis acid? What is this obvious, I think, Lewis base with its lone pairs on oxygen and its negative charge? What is forming a bond with the Lewis base? It is the H plus that is coming from this acid, nitrous acid. So OH minus is the Lewis base, H plus is the acid. And anytime you have proton transfer, Bronsted-Lowry is A for sure. We don't have any hydroxyl or H3O plus in the product side, so A is not Arrhenius. It's Bronsted-Lowry and Lewis. Anytime you have Bronsted-Lowry, the acid, Bronsted-Lowry definition, which in this case would be the HNO2, is going to be Lewis acid. It's actually the H plus with the empty orbital though, so that's the acid. The base here in the Bronsted-Lowry system would have been OH minus. It is also the base in the Lewis sense, but remember you can't go the other direction. All right, Lewis like B. B is a Lewis acid base, but it is not a Bronsted-Lowry because I don't have any protons. I have no hydrogens being transferred. So obviously the Lewis base is the bromide ion with the negative charge and the lone pairs. It is the iron ion, like we talked about before, that is the Lewis acid. That is the species with the empty orbitals. All right, C, no proton transfer here. I see a metal ion, so that tells me Lewis acid. I see nitrogen with lone pairs. That tells me Lewis base. All right, last, SO2 and water. So we are forming a bond between these to form this acid. So again, in D, no Bronsted-Lowry, we're not transferring any protons. So a water molecule is bonding to the sulfur, or the SO2. So SO2 is the acid, and water, the lone pairs on oxygen, is the Lewis base. All right, and let's see if we can't extend our page a little bit so we have a little more room. Which member of each pair produces the more acidic solution? Okay, so we are looking at some salts here, and metal salts in particular, and this goes back to that slide with the iron and the water. And what makes a metal ion more acidic is that, what you're really looking at here is ion dipole interaction. The stronger the ion dipole interaction, the more Lewis acid you're going to have going on, because the dipole is water, and it says aqueous, and your ion is the metal ion. The more interaction you have here, the more Lewis acid base-like you're going to be, and this, as we have talked about before, happens when you have greater charge. That's first. So you want to look for charge, and then you want to look for size. Small size. The smaller the ion, the more likely you are to be able to form these coordinate covalent bonds that happen in Lewis acid base systems. So zinc versus cadmium. Okay, zinc they both have a +2 charge. Zinc is a smaller ion than cadmium. All right, copper chloride versus copper nitrate. Here, copper is +1, and in this next compound, copper is +2. So it is the copper with the +2 ion that is going to be more acidic. Okay, calcium versus nickel. They both are +2, but nickel is a smaller ion than calcium. Periodic table in front of me here just for a moment. They're on the same row with the periodic table, but nickel is much farther to the right, and the size of the atom is decreasing as you go across the table. All right, that wraps up the PowerPoint. A lot of stuff going on in Chapter 16. I don't think it's as hard as Chapter 14, but we're going to do a few more problems. So let me get out of this mode. Whoa. Get us a blank page, and I'll tell you which problems we're going to do from the textbook. So we are going to do 22 from chapter 16, 24, 32, 56, 62, and 74. And that really represents a few more examples of the types of problems we saw in this chapter. I'm also going to get into when do you make the approximation. And we're going to do one where we can, and we're going to go through how to recognize that, and then we're going to go through one where we can't. So we'll have to use the quadratic formula one more time. All right, I'm going to go grab my book real quick. I always forget that. So as I do the problems, I can, read the question before we get started. All right, so if you have your book, go ahead and get it in your calculator. Maybe you can stop the video and try a few and then come back. All right, so number 22, back of chapter 16, it says, label each of the following as being a strong acid, a weak acid, or a species with negligible acidity. In each case, write the formula of the conjugate base and indicate whether the conjugate is a strong base, weak base, or has really no basic properties. All right, so in A, we have this species here. So we'll practice a little bit of how do I know whether it's an acid. Well, it's telling us they're all acids. All right, so you've got we just talked about it, a carboxylic acid. This is the simplest carboxylic acid. This is formic acid. And it is weak. It's conjugate base, so it's a weak acid. It's not one of my strongs. The conjugate of this is COOH with a -1 charge. Therefore, it is a weak base. It's a stronger base than the acid it came from, but it's still a weak base. All right, that's A. B, we have H2. Now, I know we got some hydrogen here, but it's not bonded to anything that would make hydrogen lose itself in a bond with another hydrogen. So it has negligible acidity. If you could get rid of a hydrogen, what would be left behind would be H-, and that would be essentially a strong base because it's coming from something so weak. All right, now I know it's not one of our strongest strong bases, but it would be a pretty strong base. All right, CH4. Hydrogen is not attached to anything. I mean, carbon doesn't have the difference in electronegativity here is 0.4 between carbon and hydrogen. So not very much polarity there. So we're going to call it negligible acidity. But again, if I could take a hydrogen away, I would be left with CH3-, and like the one before it, that would be a pretty strong base. HF. You think it should be a weak, strong acid, but it's not because of the strength of the HF bond. This is a weak acid. And its conjugate base, fluoride, is still a weak base, but it's stronger than the acid it came from. Okay? And then last, we have NH4+, which is a weak acid. In fact, it's the conjugate from a weak base. Its conjugate is the base it came from, and that is also a weak base. All right, so just a little bit more practice on identifying acids and bases and thinking about strength and so on. All right, let's go on to 24. All right, 24 says, which of the following is the stronger Bronsted-Lowry acid? Okay. So we've got in A, we have HClO3 versus HClO2. So you're looking for which is the stronger acid. 3 oxygens versus 1. So the chloric acid is stronger than the chlorous acid. Okay. B, we have HS or HSO4. And we've already done this question. I thought the A looked familiar, but now it's coming back a lot clearer. We'll go ahead and finish this off. But remember, when you're looking at essentially a conjugate that came from an acid, you have to think about the acid it came from. So we're looking at H2S versus H2SO4. Now, we're not being asked about the strength of the base. We're being asked about the strength of the acid. Okay, so this is a strong acid with an extremely large, not even measurable K. HSO4 is going to be weaker. The Ka2 is always going to be smaller than the Ka1. Here we have a Ka1 is much smaller than that one. Ka2 is smaller than Ka1. HS minus is going to be the stronger acid between the two because of how this is, because H2SO4 is so strong. This is very, very weak as an acid, and so therefore HS is stronger. All right, moving on to 32, and I'm going to get us another page. All right, 32. Deuterium oxide, where D is deuterium, it's a isotope of hydrogen, has a Kw, and they want to know what is the calculate the essentially the D plus, which would be H plus, and the OH minus or the OD minus at neutral pH. Okay, so this kind of question comes up, and in fact, I think it's in one of the ACS questions. So you have a different temperature, you'll have a different Kw. So what is your new neutral? When are H plus and OH minus equal to one another? So if you're given a different Kw because of temperature, or in this case because you have a different isotope, look at the Kw. It is 8.9 times 10 to the 16th here, 10 to the minus 16th. The equilibrium you were looking at, whether it be water at a different temperature or in this case deuterium. So D2O instead of H2O, and that's a liquid, just like water would be a liquid. And you have two of those to make D3O plus, that's the same as H3O plus DO minus, same as OH minus. This, of course, would not be in the equilibrium, so we're looking at equilibrium. You don't know this. They are the same because it's neutral, right? And we know if it were a regular Kw, those concentrations for H3O plus and OH minus are 1 times 10 to the minus 7, because what you're doing is you're setting this ice table into the equilibrium expression, so x squared is equal to the equilibrium constant, and there's no reactant to put in because this is liquid. So this is what you would do. You take x squared is equal to that, take the square root of that, and you have your x, or your OH minus and H plus, at neutral. So at 25 degrees Celsius and with water, x is 1 times 10 to the minus 7. For this system, it is 2.98 times 10 to the minus 8. So that's our neutral concentration of D plus and OH minus. The pH, take the log of that, is equal to, our new neutral is 7.53. So I think one of the ACS questions asks very similar. It's not deuterium, but it's water at a different temperature. You would do exactly the same thing. All right, moving on to 56. All right, 56 says, if a solution of HF, and they give you a K, is 6.8 times 10 to the minus 4, has a pH of 3.65, calculate the concentration of the hydrofluoric acid. So you don't know the concentration of your initial concentration. So let's write our equilibrium reaction. So we got HF plus water. So this is like type 3 equilibrium that we haven't really looked at I don't think, in a while, so this is good. Where I know my equilibrium concentrations of two things, and I'm going to know them. So initial, I don't know. 0, 0. Change, plus x minus x. But I've been given the equilibrium concentration because I was given the pH. So by taking that pH, I can get this and this, which will give me the x. So I'm going to erase that. That's the way I think. It's just easier to think about it that way. Set it up as if you didn't know it, and if you're given the x, then you can put it in. All right, so pH is 3.65. Taking the antilog of 3.65, I'm going to pause for a moment. Let's try that. You should end up with an H plus concentration of 2.24 times 10 to the minus 4. That's my x. So it's the same here. And that's how much I lost from my initial concentration. So my equilibrium concentration is this. And now I'm going to plug this into the K expression. I have my K, so remember, I said you can't have x's, but you can have 1. You won't have to use a quadratic or anything. It won't be complicated. So you've got 6.8 times 10 to the minus 4 is equal to, myself a little more room, 2.24 times 10 to the minus 4 squared divided by x minus 2.24 times 10 to the minus 4. Now, let me just make a comment here. Couldn't make the approximation since I didn't have an initial concentration. This K is very close to the cutoff. And when we do the next problem, we're going to have a very similar situation. And we're going to talk about whether or not we can make it at the approximation, what we need to look for. I have a little handy formula for you, and so on. But it really doesn't apply here. So we're just going to have to go ahead and do the math. So we would have 6.8 times 10 to the minus 4x minus, I did not do all the steps on my sheet. So 1.52 times 10 to the minus 7 equals, and then your 2.24 times 10 to the minus 4 squared, (5.02 times 10 to the minus 8. Okay, now add this to both sides, so take that to the other side. And I end up with 6.8 times 10 to the minus 4x equals 2.02 times 10 to the minus 7. And then divide both sides by 6.8 times 10 to the minus 4. And you end up with 3 times 10 to the minus 4, 2.97 times 10 to the minus 4. And that is the initial concentration of your acid. So I want to talk about, having given that, I want to talk about, so essentially you're just putting this here. So if you were to get if you wanted to know your equilibrium concentration minus the 2.24 times 10 to the minus 4. So remember, always go back to the ICE table. And you end up with an equilibrium concentration of, doesn't seem right, let me do it one more time. 7.3 times 10 to the minus 5. I think the question just asked for initial concentration. Let me just check. It just said calculate the concentration. So the initial concentration was 2.97 times 10 to the minus 4. The equilibrium concentration is 7.3 times 10 to the minus 5. Alrighty, that finishes that problem. A little bit different than anything we did. That's why I picked it. Now we're going to do 2 more, and we're going to talk about that approximation. All right, 62. Read the problem. The active ingredient in aspirin is acetyl salicylic acid. It gives us a formula. So let's go ahead and write that down because we need it for our little equation. All right, so we're going to go ahead and write that. Losing that hydrogen in front, so there's my equation. It's a monoprotic acid, and it gives us a Ka. So I'm going to write that off to the side. (3.3 times 10 to the minus 4. So this is very similar to the previous one in that we're kind of really right on the cutoff here as to whether or not you can use the approximation. All right, we're going to talk about it. What is the pH of a solution? So pH is what we're after. And you're given a K, so we're going to have some X's. By dissolving 2 extra strength aspirin tablets, 500 milligrams each. All right. And then, so that'll be 1,000 milligrams, that's 1 gram, in 250 milliliters of water. So, in order to even get started, we've got to get our molarity. Okay? So we got to take that 1 gram, 1,000 milligrams is a gram, and we got to add up our molar masses. Okay? And I've calculated all that. So the molar mass of aspirin is 180.17. If I take 1 gram and divide it by divide by 180.7, so 1 gram over 180.17, and then all of that is divided by the volume. Okay? All right, so that is equal to, and I'll just write right underneath here, 0.0222 molarity. So that is the initial concentration of my aspirin. No products, plus X minus X. All right, so this is what we're going to do. Got a K that's really close, so can I make the approximation? What you're going to do is solve it. Solve the equilibrium problem doing the approximation. So the math is easy. So it's 3.3 times 10 to the minus 4 equals X squared over 0.0222. So go ahead and do the math. X is equal to, when you do that, 2.71 times 10 to the minus 3. All right, so this is how you decide whether or not you have done the right thing. If you haven't done the right thing, you got to go back and put the approximation, take it out, and put the minus X back in, and you're going to have to end up using the quadratic formula. Take your X, all right, which is how much you lost of the original. Essentially what you're doing is a percent ionization. So 2.71 times 10 to the minus 3 divided by the initial concentration, which was 0.0222, times 100. If this is less than 5%, you can make the approximation. If it's greater than 5%, you cannot. So when you take the 2.71 and do that and times 100, it is equal to 12.2%. We cannot make the approximation here. So essentially, get the X using the approximation, put it over your initial concentration, so essentially you're doing a percent ionization. If that is less than 5%, so you've lost less than 5% of your acid, you can make the approximation. Can't do it here. So you're going to have to do the quadratic formula. And the fact that K was 3.3 times 10 to the minus 4 told me that we were really close to, not being able to do it. But then at least this gives you a, a way of deciding once and for all whether or not you can. Less than 5%, you can. Greater than 5%, no. All right, so it's equal to x squared over 0.0222 minus x, and that's going to have to be factored through. So that you end up with, when you take this denominator, multiply it by both sides, okay, you are going to end up with 7.26 times 10 to the minus 6. Oops. And that is 0.022 minus times 3.3 times 10 to the minus 4 minus 3.3 times 10 to the minus 4x. So that's factoring these two things right here. Equals x squared. And of course, bringing your x squared to the other side. Your c is 7.26 times 10 to the minus 6. Your b is negative 3.3 times 10 to the minus 4. And your a is negative 1. And you're going to have to use the quadratic formula. So, opposite of b, 3.34, 3.3 times 10 to the minus 4, plus or minus b squared, that 3.3 times 10 to the minus 4 squared is 1.09 times 10 to the minus 7, minus 4ac, but because a is negative 1, it's going to be plus 4 times 1 is 4 times the c, which is 7.26 times 10 to the minus 6. We'll do that math. 4ac, 2.9 times 10 to the minus 5, all over 2a. A is negative 1. All right. Solving for what's under the square root, but not doing the square root yet. Trying to do it step by step here. Plus or minus the square root of 2.9 or 2.92 times 10 to the negative 5, still divided by negative 2. All right. Taking the square root, 3.3 times 10 to the minus 4, plus or minus 5.4 times 10 to the minus 3, divided by negative 2. So you have your x plus root, and then you're going to have an x minus root. When you take these two numbers on top and add them and divide by negative 2, you end up with a negative number. Well, you can't have a negative concentration, so that pretty much says that it's not going to be the x plus root. When you take the two things on top and subtract them, you do end up with a negative number, but then you're dividing by a negative number, so that comes out to 2.54 times 10 to the minus 3. All right. And that x is your H3O plus. So if I take the log of that, I have my pH, and my pH here is equal to 2.6. All right. So I started off with 0.0222, and then I lost more than 5% of that acid. So had to do the quadratic formula, right? We're going to see this again in the next and last problem. All right, our very last problem, number 74. All right, let's read that one. My book is under my computer. Calculate the molar concentration of OH minus. So I want to know this. In a 0.724 molar solution of hypobromite ion, and they give me a Kb, so we've got a base, of 6.4 times, 4.0 times 10 to the minus 6. So that's pretty big, that's pretty small K, and we can probably, what is the pH of the solution? We can probably make the approximation, but I'm going to lead you through that, okay, just to make sure that we understand how to do that process. So I'll write our equation. conjugate base of hyperbromous acid. So this would be a problem. Let's say you had the salt, sodium hyperbromide, and you want to know what is the pH of the salt. Well, you would roll out sodium because it came from a strong. This is an anion, so it came from an acid, which is going to make it a base. You would look up the Ka for this acid, and then use the 1 times 10 to the minus 14 to get your Kb. So it could have been asked, same problem could have been asked the same way. All right, but it would have been worded differently. You're going to do exactly what I'm doing right now, which is writing the equation for the base. You got your Kb. In this case, you were given. In the case of it being asked in this way, you would be looking that Ka up and calculating the Kb using Kw, because Ka times Kb equals Kw. But we didn't have to do that. And so we have HBRO, because that's a base, and I am left with OH minus, which I always need to have if I have a base around. All right, so this is going to be pretty straightforward. 0, 0, plus x, minus x. Now, we're going to apply our little check. All right, so I'm going to solve the equilibrium. Even though I know with a 10 to the minus 6, I can probably make the approximation, I'm going to walk you through how to do it. So x squared over the 0.724. So make the approximation and solve for x. All right, x is equal to 1.7 times 10 to the minus 3. Now, was I justified in making that approximation? X divided by the initial concentration times 100, and I'm going to put it in on my calculator one more time. Is that smaller than 5%? 1.7 negative 3 divided by 0.724 times 100, and I come up with 0.24%. So way less than 5. So we were good in making the approximation. My x is my OH minus concentration. So I'm telling you 1.7 10 to the negative 3 log is 2.77. 2.77 would be a choice on a multiple choice exam. That is not your pH, that is your POH. 2 steps away from your pH if you have a base. So pH, take that from 14, is equal to 11.23. And that concludes our Chapter 16 wrap-up.